will be a distribution. Otherwise, people will say you might get lucky to got this data or just one configuration.
I agree.
Yeah, but I think once you've done this one, that one will be very easy. Just submit multiple drops and get the velocity. So you don't have to analyze the Q&A.
It's pretty easy. It's just a
Yeah, I think this one should be fine. So yeah, just add one. Oh, you got it? Okay. So yeah, a lot of work, but I think you're good. And then maybe tonight you can submit these jobs and then let it run for tonight and then get the results tomorrow. And you still have one day. And maybe you can print out on Saturday. Yeah, I probably have to pay for it first and then leave the receipt and then later on I will reimburse you for it. No. We have to do that. Yeah. So yeah, and then we could leave around like afternoon of the Saturday. I will message you about the location and time. Yeah, just ping me when you're ready for the poster and then send me for one last review.
Okay, yeah.
I might need to change the words a little bit.
Yeah.
All right.
Bye. Have a good day.
Hi, Professor. I have a question.
Oh, sorry. I hear someone voice coming out. What's up?
I have a question. I noticed that the second assignment is due tomorrow.
Wait, say again? Sorry.
So the second ANSYS assignment, I noticed that it's due tomorrow.
I'm sorry. The audio is very weak. Can you type in the chat? Sorry. It's not due tomorrow. It should be due next Friday, or next Sunday, I believe. Did I mess that up? Let me see. Well, I'm sorry. It's available starting today, and then it should be due next Sunday. So I did mess that up. So it should be due on Sunday, March 22nd. So I apologize for that. Yes. And available until the next Sunday. Yeah, thanks for catching that. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Pretty good.
Good, good. Everyone put Bengay on their hands after the midterm on Tuesday. Yeah, it was a long exam. I know. It's first exam for this class is always pretty brutal. So before we start today, so plan for today is, since the midterm was kind of very difficult, we're going to do kind of like a break day. So we're doing our second ANSYS activity today. It's going to be the bike crank activity. So this one's a little bit less time consuming. Actually, a lot of people finish this one pretty early. So, hopefully it'll kind of give you guys a little bit of break after the midterm. Okay. But before we get started on the activity, I did want to make a couple announcements with regards to the midterm. So I haven't looked at them yet. I actually gave 3 midterms exams this week, so I do need to grade my undergrads first. And so I think for you guys, I'll have the exams ready by next Thursday, which is March 19th. And so if you want to pick up your exam, I will bring them to the lecture by next Thursday. And then you can pick them up then. And I expect the grades will be on Canvas by Wednesday night, the 18th. Okay. So that's when I expect to be done. Remember that there are 2 midterm exams in this class. Okay. And remember that they have different weightings. And so remember, one midterm is worth 35% of your grade. And the other, one midterm, and the other is worth only 25% of your grade. Okay. And remember, the way that I choose, the way that I'm going to choose this, which midterm counts for higher or lower, is going to depend on which midterm you ultimately score higher. Right. And so if you don't feel like you got the score that you wanted on this exam, or feel like you didn't do as well as you wanted, remember that you can make it up on the next one. And the next one will be weighted more if you do score better. Okay. Just because I know, I think this first exam kind of ambushes everyone, just because it's direct stiffness is again, it's not the most complicated thing, but it is very time consuming. And so I think just because of the time aspect, it is difficult to kind of finish everything that you want. Okay. The other thing that I'll mention is that I don't curve my exam scores, but I do apply grade scaling at the end of the semester. Okay. And so what that basically means is that once all the final grades are in, so both exam grades are in, all your homework grades are in, final project is in, what I can do then is I can compute an overall class average in terms of their grades. Okay. If that class average is below a certain threshold, what I'll then do is I'll add points to everyone's grade until that average is hit. Okay. So I do my scaling based on the overall class average. Okay. And since this is a grad course, and I know that you guys have stricter GPA requirements, I know you have to maintain a 3.0. So usually for a grad course, I like to have a class average around 82% to kind of reach that threshold. Okay. It's usually around that 82%, and so that kind of gives you an average of around that amount. Okay. I know the first exam scores can be a little bit alarming, but just, there are mechanisms to, help you kind of bring up your grade at the end. Okay. What do we need to do to assure that we get an A in this course? It's not something that I decide beforehand. It's more just based on the quality of the work that you submit. And so, you got to just do really good on the next exam. You got to do really good on the final project as well. So final project, remember, is not going to be, it's a programming project, right? And so you're going to have to write your own finite element code for this, for the final project, and write a report. And so, you want to make sure that your code, I think at the end of the day, most people get the code to work fully. It's kind of how much time are you going to have after you finish writing the code to write your report? Because a lot of times, it's kind of clear to me when someone finishes their code and they write their report in the last hour before it's due, versus someone that comes to class a lot, and we're going to spend the last week and a half or so. It's just going to be workshop for the final project. And so, that's kind of your time to ask for help for the final code and make sure all that's good, just so that you can give yourself enough time to write the report, because the report is fairly demanding as well. I do ask a lot on that final report. And so, to get an A in the course, just got to, keep kind of doing all the work and just, just kind of staying on top of things. Yeah. Okay. Yeah. So yeah, I mean, second exam, I think I would think what I'll try to do is I'll try to provide more resources for the second exam. I think hopefully that I think will help with people. I think I'll post some extra practice, I think, for you guys to do. So just like the first exam, you'll have all the homeworks there to help you study for the second exam. You'll have all the examples that we do in class as well to kind of help you with that. But I'll probably post a past exam that I had for the second exam. I'll probably post the exam that I gave last time I taught this class 2 years ago, just so that you can get an idea in terms of the length of the exam and kind of the difficulty of the questions for the second exam, and you can use that for practice. Yeah. All right. All right. Any other questions on the grades or the exams, or just anything kind of before we begin? Yeah.
How bad is damage looking so far? I don't know if you graded.
I haven't looked at it yet. Yeah. So unfortunately, you guys are going to be the last ones I grade, and so that's why I usually try to finish the grading a week after you guys take it. But I don't, realistically speaking, and just kind of knowing, it's hard for me to work at home now because of the baby. So I don't think I'll have them graded by next Thursday.
Oh.
Yeah. So I'll have a better idea next week. Yeah. Question, yes.
Can you post the solutions?
Yes. Yeah. So as soon as I finish grading, I'll post the solutions on campus. Yeah. All right, cool. All right, so let's go ahead and get started on the activity for today. So, today's kind of a wind down day, just kind of after the intense exam on Tuesday. So today we are doing our second ANSYS activity, our last ANSYS activity, unfortunately. But today is going to be the ANSYS activity on the bike crank. Okay. So this activity, our last ANSYS activity is kind of, I always think of it as kind of like baby's first steps in ANSYS. And so, the plate with the hole is a very classical first FEA problem that a lot of people do. But, it's not really realistic. And so, you're not really simulating a plate with a hole for no reason at all, right? So our second activity here, this one's a bit more, first of all, the geometry is a bit more realistic. And the application of how we use FEA, this is going to be a bit more realistic in terms of, answering a specific question, okay? Because most of the time when you run FEA, you're never running FEA just for the sake of it, right? So you're never just running it just to create pretty pictures and pretty diagrams, even though the diagrams they do look nice. Usually you're answering some kind of engineering question. Usually you're answering some kind of, you're doing the analysis for some kind of purpose, okay? And so today, we're doing an analysis of a bike crank, which is basically the part that connects the pedal to the rest of the bike frame, okay? And so what we want to do here is we want to simulate this bike crank under a typical loading scenario. And we want to determine whether the bike crank, at least as it's currently constructed, as it's currently designed, if it's going to be able to withstand these typical forces. And, maybe find a way to redesign it a little bit better based on the results of our simulation. Okay. All right. So for this case, I'm going to leave a lot of the finite element decisions up to you. And so things like determining the mesh, determining the boundary conditions, I'll give you some hints, but I'll let you, for the most part, I'll let you guys determine that yourself. Okay. Also, for the first time, we are going to be making a custom material. So we're going to be making the bike crank out of aluminum 6061, which is a very common alloy of aluminum. Okay. And then we'll go from there. And so if you haven't done so already, let's go ahead and launch ANSYS. So remember, the way to launch ANSYS is, assuming that it's installed on your computer, we need to launch the program called Workbench. And so go ahead and search up ANSYS Workbench or just Workbench on your computer and just hit enter. Okay. So I'm going to talk for the next 5 minutes, but while I'm talking, you can kind of launch it in the background just because it takes a while to launch ANSYS sometimes. Okay. Oh, and if you haven't done so already, so the geometry for this project or for this activity is on the Canvas site. And so if you go to our Canvas page, you go to the activity page, go ahead and download the crank file for this activity as well, okay? All right. Okay. So one of the big differences you're going to see in this activity compared to the last one is that, we're not going to draw our geometry from scratch. I'm actually going to give you the CAD file and you're going to load that within ANSYS itself. Okay. So this is a bit more typical in terms of how ANSYS is typically used. So a lot of times, we're not creating CAD files from scratch within ANSYS. Usually you're creating the CAD file in another software like SolidWorks or AutoCAD or something like that, and then importing it into ANSYS to do the analysis, okay? So this emulates that exactly. So you're going to download the CAD file and then import it within ANSYS, okay? Okay. All right, so that's kind of the goal for today. So compared to the last activity, I'm not going to be up here talking all too much just because the process is more or less going to be the same. So we're basically going to be, doing our geometry, doing our meshing, doing our boundary conditions, and doing the analysis from there. And so one big thing you're going to see here is that I'm going to have you do a lot more with the results here. So I'm going to ask you things like, analyze your results, predict things like the maximum force that it can withstand, and things like that. Okay. Okay. So was everyone able to open up ANSYS and open up Workbench? Okay. Okay. So let's go ahead and bring over Workbench here. Oh, midterm one related question. Let's see. Okay, considering it's no one really finished, would this first exam be a lower average that would get bumped at the end through the grade? Yes. Yeah. So that's the whole purpose of the grade scaling is that for a case like this, where the exam was pretty tough and the average was lower, that's probably going to lead to a higher amount of grade scaling at the end. Yeah. But of course, this does give you time to, make up the exam for the second midterm, make it up on the final project as well. But I think overall this is going to lead to more grade scaling at the end. And so if you want to, I don't know how many points I'm going to add right now, just because it's still pretty early in the semester. And generally for this class, the first midterm exam is kind of the low point. And so generally after this, people tend to do much better on the second exam. People tend to do much better on the final project. So I actually think last time I taught this class, I think I only applied like maybe 1 or 2 points of grade scaling at the end. Even though the midterm one average was probably around like 65%, I think last time. And so, so there's a lot of time to make it up. Okay. If there's someone with a crazy grade, would they get taken out of the scaling calc? No. So if they exceed 100%, they just get an A. So there's nothing past A. But if you're asking, do I take them out of the average? No. So I just take the average of everyone in the class. Yeah. But the class is big enough for, usually one outlier is not going to ruin the calculations all too much. Yeah. Usually. But I'll look at the data, and if there is a few outliers, then I'll take that into account. I'll think about it. Okay. Mm-hmm. Okay. All right. So let's go ahead and open up ANSYS here. So let's go ahead and open up Workbench, and then just like last time, let's go ahead and create a static structural analysis. So let's go ahead and click and drag static structural and put it over here. Okay. So it's a little bit unfortunate in this class that, this class is we don't do too much ANSYS because there's so many other analysis types here. So there's obviously a lot more we can do with ANSYS, but for at least our purposes, we're just going to do static structural. Okay. Okay. So first thing we're going to do is we're going to add in our material properties. So if you remember last time, the way to look at the material properties is we're going to double click on engineering data. So let's go ahead and double click on that. Okay. And we open up our engineering data table here, okay? So by default, remember ANSYS only loads a single material into our docket here, which is structural steel, but we want to add a new material here. As we look back at our activity here, we can see that our crank is made of a specific alloy of aluminum, okay? And we're given the material properties here. So it has a Young's modulus of 1 times 10 to the 7th PSI and a Poisson's ratio of 0.33. Okay, so there are a couple ways to add new materials here. And so on the one hand, if you have a fairly common material, it's probably already implemented within ANSYS. We just have to add it to our project. And so for those cases, you can click on engineering data sources right here. Okay, so there's kind of a button up here with kind of some books next to it. So this will open up or give you access to the library of materials that are within ANSYS itself. Okay. Okay. So there are several libraries of different materials here. So there is ANSYS Granta materials data for simulation, right? And so there are lots of materials here. There are general materials, and so these are kind of materials that have kind of a lot of applications here. So we have things like we have aluminum here, concrete, copper, cast iron, magnesium. Okay. They even have a package for additive materials. So this is your 3D printing materials. This is pretty interesting. The fact that they have it as part of the educational license, that's kind of pretty cool. Geotechnical materials, composite materials, nonlinear materials, explicit materials, hyperelastic materials. So there's actually quite a lot of materials that come packaged within ANSYS. And you can kind of see why a lot of these materials, they're not loaded by default, just because there's a lot to go through, a lot of possible ones here. Okay. And so usually, if you're doing just a basic kind of static structural analysis, a lot of times you'll be adding materials from this library called general materials. Okay. And so if you look here, there is, different material. Here's our structural steel. There's even stainless steel here as well. Okay. Titanium, polyethylene, magnesium, cast iron. And so if you look at aluminum, right? So if you left click on a material here, you can actually look and see its properties down here at the bottom. Okay. Now let's check and make sure. So let's see if this aluminum alloy has material properties that match what we want to do for our analysis here. Okay. So we want our material to have a Young's modulus of 1 times 10 to the 7th and a Poisson's ratio of 0.33. Okay. So if we come back to Workbench, we can see here that the Young's modulus of this aluminum alloy is 7.1 times 10 to the 10th Pascal. Okay, so let's go ahead and change the units here somehow. So let's change the units here to US customary. I think that one gives us PSI. Okay, so the units is up at the top here. That did not change it. Let's see. I think they changed it. I think they changed the interface here. It used to be that you could kind of update the units and kind of see. Oh, let's see. Here we go. Okay. So if you want to change the view of the units here, you would have to change the units up here to whatever units that you want, and then you have to click on this check mark here called Display Values in Projected Units. Okay. Or Project Units, excuse me. So I think that was an update they made on the most recent version. Okay. All right, so if we look at our Young's modulus for our aluminum alloy, you can see it's very close. Okay. So we're looking for a Young's modulus of 1 times 10 to the 7th PSI. That's how much we want for our project here. And then in ANSYS, it gives us a Young's modulus of about 1.03 times 10 to the 7th PSI. Okay. So it's about 3% off of where we want to be. So this is pretty close. And so, it depends on how close you want to be. But if that's close enough to you, then you can just click on this plus arrow here and add that to your project. Okay, so to add a material to your project, you just click on the plus arrow and then it adds it there. Okay, so to check and see if the material was added to your project, you can go ahead and exit out of this library. So to exit out of the library, you left click on the book here, Engineering Data Sources, and you come back to your library here. So now we have 2 materials, one of them being aluminum alloy and the other being structural steel. Okay. Okay, so that's one way to add a material. And so if your material is already built in within ANSYS, I would say that's generally the most convenient thing. But there's another way we can kind of manually add the materials in that I want to show you as well. But for now, was everyone able to add aluminum alloy to their project using that method there? Good. Okay. So the other way we can add a material is we can click on this box here to click to add a new material, and we're basically going to add our material custom. Okay, so let's go ahead and click there, and then we can go ahead and define our new material. So let me call this just so it's unique. We'll call this AL6061. Okay, all right. Right, and now we're free to add in our material properties as we want. Okay, so to add specific material properties, you can see right now it's completely blank. Okay, so we need to basically define which material properties that we want to add in, and there's lots of different material properties that we can do. So we can add in, hyperelastic material properties. We can add in things like density. We can add in geomechanical properties. or viscoelastic properties, right? But for a general material here, where we're just doing a static analysis, the only materials that we need are linear elastic materials. Okay. So in particular, we want to add a basically isotropic elasticity of this material. Okay. So with your new aluminum highlighted here, go ahead and double click on isotropic elasticity. Okay. That way we can now define the Young's modulus and Poisson's ratio of our material. Okay. So for the Young's modulus, let's go ahead and enter the amount that we want, which is 1 times 10 to the 7th. You can just enter 1e7. Okay. And then our Poisson's ratio here is going to be 0.33. Okay. Okay. And so with that, our material here is fully defined. And so, we've only defined the isotropic elasticity. But if you want to add things like density and, viscoelastic properties, you can do that as well. But that's kind of the basics of making a material from scratch. Okay. So for this particular activity, you can use either one. You can use the pre-built aluminum, or you can use the one that you just defined here. But since this is our last ANSYS activity, I did want to show you kind of both methods of adding a new material. Okay. All right. Any questions on this? Okay, good. Okay. All right, so let's go ahead and come back to the project. So let's go ahead and close out of the engineering data. Right. All right, so next thing we're going to do is we're going to add the geometry to the project. Okay. So remember, in this project, we're not going to draw the geometry. We're just going to simply import it from the file that we just downloaded. Right. So to import a geometry, you're just going to right-click on geometry here. Okay. And then you're going to go to this option here for import geometry. Okay. Now, import geometry is going to allow you to basically browse. So let's go ahead and click on browse. Okay. And then we're going to add in the crank file that you just downloaded. Okay. Okay. So remember, so the crank assembly is the file that's available for download from the Canvas site. So let's go ahead and add that in. Okay. So if you're on the lab computers here, it's going to display as a SolidWorks object. But it's actually not a SolidWorks part, right? And so it's actually actually if you go to the file itself, I'm just going to show you really quick. Okay. So I think it defaults to SolidWorks just because, we teach SolidWorks in this class. But if you look at the properties, okay, you can see that the file extension for this is actually x_t. So, again, this computer thinks it's SolidWorks, but it's not. So x_t is the file format called Parasolid. So Parasolid is actually kind of a separate company from SolidWorks, or I guess a separate standard. And Parasolid is actually used among a lot of different softwares. Okay, it just opens up in SolidWorks here just because this computer uses SolidWorks a lot. Okay. Okay. And in fact, questions.
When importing geometry, does it matter the type of file that we?
It does, yes. And so ANSYS can work with a lot of open source file formats. So like Parasolid, it can work with a step file, so STP or STEP. It can work with an IGES file, so that's IGES. The one format that it can't do is actually SolidWorks part. And so if you have a SolidWorks part or SolidWorks assembly, you actually can't import that within ANSYS. So I think one company is trying to buy the other, and so until that happens, then they don't talk to each other. So if you do have a SolidWorks part that you want to import in ANSYS, you do have to convert it to one of these other file formats. Yeah. Generally, I recommend Parasolid. Parasolid is one of the most stable, and there's the least likely for weird things to happen with Parasolid. But step files work as well. STL file can work in a pinch, but STLs are usually not well suited for this. Yeah. Mm-hmm. Okay, so let's go ahead and import the crank assembly. It should be very quick. So let's go ahead and double click it. And so doing so, you can see that we've imported it. And you can see the icon next to geometry has changed as well. So now it's P for Parasolid. Okay. Okay. All right, so that is the import. All right, so once you have your geometry import, you should have a green check mark next to geometry. So let's go ahead and open up ANSYS Mechanical. So let's go ahead and double click on model here. Okay. And we're going to open up ANSYS Mechanical. So that's where we're going to apply the mesh. That's where we're going to apply the boundary conditions. And then we'll go from there. Okay. Okay. All right. So if all goes well and your import is good, after you open up ANSYS Mechanical, you should be able to see your part within the graphical user interface. Okay. All right. Everyone able to kind of get this part here? Everyone able to open up and see the bike crank? It probably takes a minute or two to open up ANSYS. It's not known for speed, that's for sure. Okay, everyone able to open up? Good. Okay. Okay. All right. So here is our bike crank, and what you can actually see here is actually an assembly of 3 different parts. And so we have the main body of the bike crank. Let's see, the main body, right? So this is the main body of the bike crank here. We have the pedal. So the pedal is just kind of the cylinder that's kind of jutting out here. And then we have kind of an adapter ring that kind of fits inside there, so the pedal can mate with the pedal, okay, with the bike crank, excuse me. Okay, so for an assembly of parts like this, what you can actually do is that you can actually suppress different parts if you're not going to need them in the analysis, okay? So this is very common. So, oftentimes in finite elements, you'll be given an assembly of parts that's way more complex than what you need, right? Because a lot of times, when engineers or designers kind of make these CAD files, they're not making the CAD files to do analysis on, and so they're doing the CAD files to get every detail in terms of the manufacturing and things like that. Okay. But one thing with finite elements and with any computational analysis in general is that usually when you add more details to your simulation, it actually makes it more difficult to run. Okay. And a lot of times, you add that difficulty kind of unnecessarily. And so, you kind of just make things difficult kind of for no reason, right? And so a lot of times, when you get these assemblies, you want to suppress some parts and remove them from the analysis just to give yourself an easier time with the analysis, okay? And so one example here, so for this analysis here, we're most interested in whether the bike crank is going to fail or not, okay? That's kind of the design question that we're answering. And so in that sense, we don't really care what's happening with the pedal, and we don't really care what's happening with this adapter ring too, okay? So let's go ahead and suppress those parts just so they're not taking up mesh, they're not taking up they're not taking up space in our simulation, okay? So first thing we'll suppress the pedal. So let's go ahead and right click on pedal. So you can find it by kind of clicking this plus arrow next to geometry. Okay. All right, so to suppress a part, let's go ahead and right click on the part, and then you're going to go down to this option here called suppress body. Okay, so go ahead and click that, and after you do that, you can see that that part of the geometry is no longer there. Okay, now you can unsuppress it. It's not like you deleted it; you're just kind of hiding it. And so to unsuppress it, you just right click it and then unsuppress, and then it's right back. Okay. Okay, and then let's do the same thing for this, this little adapter ring here. It's called part 9 assembly 2 rev X 0.375. So let's go ahead and suppress that one as well. So then all we're left here with is just the bike crank. Okay. Okay. All right, any questions on that? Everyone able to suppress that part? Okay, good. Okay, so next thing we're going to do is we need to assign material properties to our bike crank. Okay, because remember in this project document we said that this bike crank is made out of aluminum, and so let's go ahead and assign that material property here so we can run the analysis. Okay. Okay, so to assign a material to a particular part, what you're going to do is you're going to left click that part in the geometry portion up here. Okay, and then you're going to go down to the bottom left hand side of the screen. And you're going to see that there's a setting here for material assignment, okay? So right now, the material assignment is structural steel, just because that's the default. But let's go ahead and change this to aluminum, okay? So remember, we have 2 choices of aluminum here. You can use the built-in aluminum, or you can use the custom aluminum that you made yourself. Okay, so I'm going to use the built-in one just because it's, it's already built in. But for this activity, it doesn't really matter which one that you choose, okay? Okay, good. All right. All right, so now our geometry is ready. We have our material properties set. So now we can go ahead and move on to the mesh. Okay. Okay. So the mesh here, so actually, the mesh is actually fairly straightforward. So I think I'll do it together with you, and then I'll have you do the boundary conditions yourself. Okay. So for the mesh here, we have a pretty straightforward part. And so all we're going to do here is we're just going to assign a size. Okay. So remember, just like we did in the last activity, you're going to left click on mesh. And then in the bottom left-hand side of the screen, you're going to click on size. Or I'm sorry, you're going to go to element size here. Okay. Okay. So right now it's using the default size, but let's go ahead and specify something. And so let's specify an element size of, let's see. We see kind of how big this part is. Right, so I'm going to use this ruler down here to kind of estimate the size. There's a question in the chat. Question, the materials don't seem to be loading when I click assignment. Do you not have any materials there at all, or do you just have structural steel? Oh, okay. Let me come back to you. So let me get to a good stopping point, and I'll come back to help you. Okay. All right, so for the mesh here, let's go ahead and set the size. And so, we have basically a bike crank that's about maybe like 200 millimeters long. So let's go ahead and set an element size of, let's try 25 millimeters to begin. Okay, let's see how that looks. Okay, so when you have your mesh, go ahead and right-click generate mesh. Okay. Okay, so with the mesh size of 25 millimeters, we get a mesh that looks like this. This is pretty awful, not gonna lie. So this is a pretty awful mesh just because it's very coarse. So let's go ahead and refine this mesh. Remember, our mesh here determines our accuracy. So the finer our mesh, the more accurate our results are going to be. So let's set our element size here to 5. Let's see what that looks like. Okay. Okay, so with 5 millimeters, we're doing a little bit better here, right? But it's not really where I want it to be. Okay. Okay, so let me give you kind of one kind of rule of thumb that you can use for meshing. So meshing is actually a very complex topic. And so, you could spend weeks talking about meshing here. And so, there's a lot of opinions in terms of what's a good mesh, what's a bad mesh, and everyone kind of has a hot take on that. But one good kind of rule of thumb that you can use for meshing, especially if you have like a relatively slender part like this, is you want to see how many elements are through the thickness of your geometry here. Okay. So one thing I'd like to do, and one metric I always check for these types of simulations is I kind of look at the thinnest dimension of your mesh. And what you should see is that you should have more than one element through the thickness of the mesh. Okay. Now, what that means basically is that you should have more than one layer. Okay. So you should not have an element here that kind of stretches from one end to the other end. Okay. So which obviously we do here. So you can see we have this one element here, this triangle that kind of stretches from one edge to the rest. Okay. Now you don't want that because what happens then is that you have no interior nodes along this edge right here. And so that can lead to a lot of inaccuracies. Okay. What you want instead is you want something that kind of looks like this instead. Okay. So you can see here that we have, I call this kind of 2 layers of elements through the thickness. We have one layer that kind of one element that kind of comes halfway up and another element that kind of goes the rest of the way. So we at least have one interior node in between the two. Okay. So, one interior node is not bad. It's not the worst thing, but, generally you want to have more elements through the thickness. Okay. So let's go ahead and refine this one more time. So let's go ahead and refine it to maybe 2 millimeters. And let's see what that looks like. Okay, so with 2 millimeters here, you can see that we're doing much better here. Okay, so you can see that we have more elements through the thickness here, and this is going to give us a much higher quality result. Okay? And you can go even further down, right? And so even with 2 millimeters here, we're kind of pushing it a little bit. But let's go down one more. So let's go down to 1 millimeter and see what that looks like. Okay. So with 1 millimeter, this is a little bit overkill, right? And so if you look at the statistics for this mesh, you can see we're at 39,000 elements. So for a tiny little bike crank like this, that's a little bit overkill. I would say you don't need that many. So let's just go back up to 2. I think 2 kind of gives us a good balance here. Okay. So 2 is pretty decent, right? And so that gives us, a decent mesh. It's not too expensive, right? So the number of elements is not too large. But it does at least give us 2 elements to the thickness, which is good. Okay. All right. Any questions on the mesh here? Okay. Okay. So the next part, I'm going to have you guys work on your own while I kind of go around and kind of help debug people that are having issues. But if you go to the project, if you go to the activity document here, right? We've done problem 1. So problem 1 is a mesh. So that's done. Okay. So problem 2 is loads and constraints. Okay. So you're basically going to be adding loads and constraints, forces and fixed supports here as it's needed. Okay. So I'm going to let you do this yourself, right? The only requirements that I have is that you must have at least 1 fixed support. So 1 plus fixed support. And you must have 1 location where a 100-pound force is added to the bike crank. Okay. So you must add those 2 boundary conditions to your model. Okay. Now, where you apply them, I'll kind of leave it up to you. But remember, you're modeling a realistic situation here. Okay. All right. So let me give you some additional context here, just to kind of help you kind of choose where to put these here. Okay. Okay, so here's our bike crank. And so what you can expect is that this side of the bike crank with the 3 holes, this is where the bike crank attaches to the bike. Okay. So the bike frame is on this side. Okay. The other side of the bike crank, remember, this is where the pedal was. We suppressed the pedal, but that's where the pedal was, right? So this 100-pound of force, right? This is meant to emulate the force of someone pushing down on the bike pedal. Okay. All right. So I'll kind of leave that up to you, right? And so not only do you have to determine the location of the force, but you have to determine which direction the force is going to go as well. Okay. So you can do it in the Y direction, you can do it in the X direction, you can even do it in the Z direction. Okay. Think about, what kind of makes the most sense in terms of, the direction of the force. Because remember, we want to simulate the worst possible case. Okay. So think about, which direction of the force that you want to apply. That's going to result in the biggest deformation and the biggest stresses within the bike crank itself. Okay. And by the way, there's no wrong answer here. And so, there is a correct answer. Let me rephrase that. But I'll go over the correct answer, in a bit. But for now, I'll let you guys kind of, work on that yourself. While I kind of go around and kind of help people out with their simulations here. Okay, Marley, so let me come back to you first. So you said that you don't have any materials. Did when you go back to Workbench and you click on engineering data here, do you see the materials here from Workbench? Okay, so material right under materials tree. Assignment. Let's see. Okay. Okay, so when you go to geometry here, you click on this and you click on assignment. So when you click on this box is empty right here. That's what you're saying. Okay. But when you go back to Workbench, all the materials are here in this table when you click on engineering data. Oh, that is very strange. Every year it's always a new issue with ANSYS here. Might be a bug, kind of a concerning bug, just because it's it's a pretty core feature. Okay, yeah, that was going to be that's good. That's always going to be a good thing to check. So when you click under the materials tab here, do those materials show up here? When you click this plus arrow next to materials. Oh, interesting. They show up, but you can't assign them. Interesting. Huh. That's very strange. Can you show me? Can you share your screen? If that's possible. Let me give you privileges to share screen. Okay, let me look at this. I'll just look at your screenshot. You don't need to share your screen. Oh, okay. Oh, it's just a complete blank box. That almost kind of seems like it's trying to load, but it's not loading for some reason. I wonder if it's an issue with with RAM or something like that. Hmm. Okay, I would say for now, if you can create a mesh and do the boundary conditions, let's just do it in structural steel for now, and then maybe later we can try to change the materials again. I think there are different ways to change the materials, but you may have to do it for in another different way. But I think for now, just doing it in structural steel is fine. Yeah. Yeah. So Marley, go ahead and create the mesh, and then create the boundary conditions, and then we can go from there. Yeah. Mm-hmm. Okay, I'm gonna make my rounds here.
Okay, so I have the opposite problem of Norman,
Okay.
where my materials are not good.
Oh, okay. So, but it's in the workbench?
Yes, but here's the catch. So for whatever reason, it wouldn't open.
Okay.
So what I did is I opened Workbench myself, and then I put import geometry just to get it started.
Yeah.
And I was assuming that that Workbench and mechanically kind of connect the two dots, but I don't think it did.
Okay. So don't put engineering data. Let me see what's in there right now. Oh, it's frozen.
Yes.
Well, has it been frozen for a while?
No, so I don't know when it finished or when it thought it was finished.
Yeah.
Yeah.
Okay. I'll go back to the mechanic. Oh, okay. So that's a different issue. So that you have to reset the display. So go ahead and put it, and then reset workspace. There we go. And then now you can so I think moving now should be. So, yeah. Okay. We'll put it on the plus.
I only wondered what it was well for, and then you start over. Because I do remember what we did.
Yeah, you could do that. Yeah, it looks like it's stuck starting mechanical. So it's yeah, it's a RAM problem. Fortunately, RAM is like $1 trillion.
Yeah.
Okay. Well, yeah, try to exit out of it and then restart it, and then we can try closing the mechanical first. Okay, I'll come back.
Okay.
Yeah. How you guys doing? Good. Do force minutes because it's 100 pounds. How you guys doing? Good.
I don't know if you remember.
Oh, good.
Yeah.
Oh, good. Let me go ahead and add my own boundary conditions here.
Oh, gotcha.
All right, how's everyone doing? Good. Okay. All right. So I'm just gonna. I know some people are still kind of catching up, but there's a lot of kind of extra time in this activity. So let's just go ahead and keep going for now. Okay. So if you want to see how I implemented these boundary conditions, so I applied a fixed support on the left end, basically where the three holes are, because this is where this bike crank attaches to the bike, right? Now I know in reality this is not a true fixed support because the bike crank is going to be in motion. But in general, when you apply a fixed support boundary condition, usually you're going to apply that at the location where your part is attached to something bigger. Okay. So you're going to have situations where your part's actually fixed to the ground or bolted to the wall or something like that. So those are pretty obvious where you're going to apply a fixed support. But in this case, this bike crank is going to be attached to a larger bike frame. And so relative to the bike frame, this bike crank is going to be pretty stationary. And so that attachment point, we can act as a fixed support. Okay. For the other boundary condition here, we're applying a force boundary condition, right? And I'm applying it on the location where the pedal is. Okay. And in particular, I've applied my 100-pound force in the negative Y direction. Okay. All right. And so the reason I'm doing that is because, I'm looking at a situation where the bike crank is kind of horizontal like this. And basically the person is stepping down on the pedal, applying a downward force just like that. Right. And so we have 100 pounds of force being applied downwards just like that. Okay. Now, another option that I see people have done in the past is they've applied a compressive force. So they applied a force in the negative X direction. That's also valid. So that'll also create a stress in the part. But if you're talking about the direction of force, which is going to cause the most deformation, is going to cause the most stress, bending is always going to produce more stress than compression. Okay. So if you ever have kind of a beam-like structure like this, right, and you want to find the direction of force that's going to cause the most damage, you always pick the bending direction. Okay, because by applying the force in this direction, it's going to cause the bike crank to bend down this way. Right, and then you're going to have some bending stresses. You're going to have tensile stresses up top, compressive stresses on the bottom, and that's going to be much greater magnitude than just a pure compressive force. Okay. Right. I've seen people also apply the force in the Z direction when I've run this activity in the past. Technically, yeah, that's also a bending direction, so that'll put the bike crank in bending, but that's not exactly realistic because no one is pushing their bike crank from the side like that. Okay. Right. So when you're doing these finite element analyses, you want to put the boundary conditions in kind of usually in the worst possible case, just because a lot of times you're doing failure analysis. But you also want to be realistic too. So you don't want to put things in a weird spot. That's not going to be realistic. Okay. Okay. So now that we have our mesh, now that we have our boundary conditions, we are ready to solve. And so to create a solution, you're going to right click on solution A6. Right. So that's going to go ahead and insert our total deformation. Let's go ahead and insert our equivalent stress. Okay. Let's go ahead and run it. Okay. Wait, for some reason it's taking a long time. Okay. All right. So after you run your simulation, you should get some results. Okay. So you can see here that we have our deformation here. Actually, I want PSI. There we go. Okay. So you can get your equivalent stress. You can get your maximum deformation. Okay. So you can see here that we have a maximum deformation of about 0.05 inches, and that occurs at the very end. So that makes sense, right? Because that's where our force is being applied. So, and we have our fixed support here on the left. And so it makes sense that the deformation is maximum on the right. Okay. In fact, you can play a little animation of the bike crank deforming. Okay. The animation doesn't do anything. It's just for fun. And so, but you can do that if you want. Another thing you can display here is your equivalent stress. Okay. Now the stress is going to be important because ultimately we're going to run a failure analysis on this bike crank. Okay. So from the stress analysis here, you can see the locations where the stress is maximum. Right. So you can see the stress is maximum at the top and at the bottom here. right? It's a little bit hard to tell from the equivalent stress because equivalent stress is kind of like stress and magnitude. But at the top here, we have basically a tensile stress, right? And on the bottom here, we have a compressive stress. Right? As we typically expect in bending, okay? Okay, and then the other thing to see here is that the maximum stress magnitude, you know, yours is going to be a little bit different. So if you don't get this exact number, don't fret. Especially if you use a different material property, right? So remember, I'm using the built-in aluminum alloy that ANSYS has. But my stress magnitude here is 13,712 psi. Okay. Okay. All right. And so that's the activity, right? And so last thing you're going to do here is you're going to do basically this question here. So we've basically done everything up until this point, right? So next thing I want you to do is, and kind of the last thing I want you to do with this activity is to compute the maximum load that this bike crank can sustain before being in danger of failing, okay? Okay, so for this part, we're going to assume that our material here, our aluminum, has a yield strength of 35,000 psi. And what that basically means is that the stress in our bike crank can get all the way up to 35,000 before the bike crank will fail, okay? And we're going to work with the factor of safety of 2, okay? And so the way we're going to use factor of safety here is that, you know, we're going to take our maximum yield strength and then divide it by the factor of safety. Okay, so we're going to take 35,000 and divide by a factor of safety, which is 2. And so that's going to give us a maximum stress of 17,500 psi. Okay. Okay. So under these conditions, under these design constraints, we can say that our bike crank can sustain up to 17,500 psi. Okay. So the first question we're going to ask is, you know, is our bike crank safe? So since 13,712 is less than 17,500, we can say that yes, for a 100-pound force, you know, our bike crank can sustain that. And we can, you know, it'll be safe even with our fairly aggressive factor of safety. Okay. Okay. And so for this part right here, I want you to find out what the maximum load that the bike crank can take before it yields. Okay. So I want you to go in, right? I want you to go in to your force boundary condition. Make sure that you're in bending here. So make sure your force is in the y direction. And I want you to change this force, right? I want you to increase it until you reach a point where the stress is about 17,500, okay? So instead of minus 100 here, let's go ahead and increase it. So let's make this 105, okay? Okay. Right, so I increased the load from 100 to 105, and we can go ahead and run our simulation one more time. And then wait 2 minutes for whatever reason, even though this is a simple case. You may want to coarsen your mesh if it's taking a while. Okay. Okay. All right, so you can see that after increasing my load to 105, now my stress is 14,397, which increased. Okay, so I basically want you to keep increasing the force and basically find the amount of force that the bike crank can take before we reach the stress of 17,500. Okay. And by the way, you know, don't waste your time trying to get exactly 17,500. It's very hard to hit this on the nose. And so as long as you're within maybe like, maybe like 17,600 or 17,400, you know, as long as you're kind of in that range, 17,600, 17,400, okay? So as long as you're within that range, I'd say that's close enough. So, you know, don't waste an hour, you know, chaining the force by, you know, 0.1 pounds until you reach 17,500 exactly, right? So as long as you're in the right ballpark, right, you're within 100 psi, I would say that's close enough. Okay. Okay, so you can go ahead and work on that for the rest of class today. So you have about 20 minutes. Okay, but that's not the only part of this activity. And so if you remember, you know, it's been a while, but you know, a couple of weeks ago we developed our MATLAB code to solve frame problems, right? And so one part of this activity is I also want you to use that code to basically solve this frame. This is a frame from the homework. Okay. So remember, don't solve this by hand. Basically, you want to input this in MATLAB to solve it. Okay. And then the last part of this activity, probably the part that's going to take up the most time, is I want you to implement a 2D truss code. Okay. So remember, we kind of talked about this a couple of weeks ago, but I want you to basically take the methods and take the methodology that we use for the frame code, and I want you to write another code that implements the solution to a 2D truss. Okay. And I kind of walk you through the different steps here in steps A through F. All right. Okay. All right, and so I think I don't think let me see. Did I post the frame solution code? Let me see. I don't think I may have posted it just yet. Okay, I didn't post the solution for the frame code just yet. So I'm going to do that when I get back to the office. So I'm going to post a solution for the frame code. You can use that to solve for the problem 6 on the activity. And then you can use that as kind of like a template or kind of like a guide to implement the last part of the homework here. Okay. All right, so this activity, there's 2 parts to it. So there's the ANSYS part, and then there's the MATLAB part. But you have the rest of the class to work on it, and of course, until next Sunday to complete everything. Okay. Any final questions before I let you guys go and start working? Okay. All right. So for the last 20 minutes of class today, I'll kind of keep making my rounds, and so if you're still kind of having issues with the ANSYS, or if you have questions on the MATLAB, you can go ahead and ask. But that's it for me. I don't have any more content planned for today, so you guys can take off if you want. So thank you guys for coming today. Remember your midterms, I'll have them graded by next Thursday. So make sure if you want to pick them up, come to class next Thursday. And I will see you guys then. Hope you guys have a good weekend.
I had to go to clear and reset the computer because it was stuck in a loop, and I figured out why I couldn't load the task hunter. Because it's disabled by the administrator.
Oh, okay. Yeah, they don't let you do that for these computers. So.
Yeah. So
is it working?
Yeah.
Okay.
I was able to import everything, so everything's working now. I just got to put everything.
Okay. Good. Yep. Okay. Good.
I'm having trouble switching direction of this arrow.
Okay. Yeah. So the easiest way to do that is when you go to the force here, go to define by. Yeah. So instead of vector, you can change vector. Oh, so now you can define the next one components. And you also want to change the length. Right now, the looks like this. So we're applying 100 pounds. Yeah, that's nice. Yep, yeah, thank you. Got it. Good. Almost. No, just a car module. Oh. How you guys doing? Good. Okay. Yeah, so you can do STP. That one usually pretty solid. You can save it as an IGS as well. So IGS works. But the one I like to use a lot is called X_teams. IGS will work. Parasolid works as well. That's the one I have. So the file that it should already be in Parasolid format. So you it's already. Yeah, so Parasolid is compatible with SolidWorks, obviously. It's also compatible with I think most CAD software should hold Parasolid. I was telling someone else earlier that yeah. So the CFP code that I used to work with in that school, we use Parasolid. We moved away from it just because the file format is free, but the interpreters are not. So they kind of protect that behind. So yeah, we stopped using Parasolid. It is good format. Yeah. So go to and click on folder and Emacs. Yeah, so it's already shown at the max image. Go to any part, it can show you. So yeah, so normal stress, if the stress is positive, that's the tensile stress. Negative normal stress, that's the. Yep. Right. Yeah. Go to that's your custom. Let's go back to the bench. Okay, Yeah, so you put the material as 1 ton instead of Pascal, but this needs to be PSI. So I would say the easiest thing is because we have the limit at level. Okay. So just go back to yeah, so go back to ANSYS. And then just change this to we'll go right here. Just change that to and now stands for non-linear, although it's not really relevant for
Those not necessarily like where's that one?
yeah. So normal stresses are, I think of them as kind of forces that are kind of either trying to pull apart the material. So normal stresses are kind of the opposite of shear stress. Shear stress is kind of trying to shear the material from like this, kind of shear the wire. Whereas normal stress is kind of pull it.
So this one we're basically seeing what it's gonna be like.
Yeah. So actually, we're doing a bending stress. So when we apply the force here, so the top here is going to be in tension. So like if you take like any rod, you bend it, like the top is going to kind of pull apart.
Yeah.
So that's a tensile. Whereas the bottom part, the top part's pulling it away, except the bottom.
Yeah. And that's what we're seeing by the
So that's a difference. So if you were to take like a rod and you would try to shear it, so basically you kind of hold it like this and try to go back like that would be a shear.
And basically when we produce that force down there, it's mostly not really producing a lot of shear.
Exactly. Yeah. It's usually very hard to rip a material by shear, unless it's in a very specific situation. So most things are going to fail from normal stresses first, especially in a typical case. It's fine because shear strength is actually much less than normal strength. But yeah, there's just not that many situations with shear.
Would that just be done by maybe like theoretically, like just like
yeah? So that's different. So that's 40.
Okay.
Yeah. So that's another strength.
Thank you. Yeah.
All right. Thanks, guys. Have a good weekend. Yeah, so I'm going to upload the code. Basically, when I go back to my office, I'm going to upload it. So it'll be where you can find it. So you go to files on our Canvas page. You go to code. So it'll be in here. But I'm also going to put it on the page for week 8 and week 9. So if you go to the week 8 page, I'm going to put it under files here, and then for week 9, I'm going to put it there as well. Yep. All right. Thanks, Lewis. Have a good weekend. All right, everyone. 6:45. It's time to head out. So so this activity member is going to be due next Sunday. So not only the ANSYS part, but also the MATLAB part as well. So just like I mentioned, you can look forward to the frame code being uploaded basically in maybe about 15 minutes when I walk back to my office. So you can use that to answer problem 6, and then that will serve as your starting point for problem 7 as well. Okay. So remember, on the activity document, there is kind of a step-by-step instruction on how to write the truss code. So I would definitely start there. But of course, if you need help writing the truss code, I'm always available through email or office hours as well. So don't be afraid to come ask. Okay, because it's, even though I have it step by step here, it is still kind of a big thing to kind of write your own code from scratch. And so make sure you kind of get all the help you need. Okay, so thank you guys. Hope you guys have a good weekend, and I will see you all next week. Thanks.